project and what kind of method you are going to use. And then in the introduction, gives a brief story about why you choose this method. Choose this topic, and how do you solve the problem. And some brief stories about the topic, okay? And then what is the method you are going to use to solve the problem? And then the expected results. Now the thing I want to remind you is, your term project is not just copy the contents of the paper, okay? You have to regenerate the results. What do I mean by that? You have to generate signals. You have to generate signals first, and then use the method proposed by the paper, okay, to solve the problem, to produce the result. And hopefully your results are quite consistent with that given by the paper, okay? That is the most important thing. So one more time, let me remind you, that your term project is not just to copy the paper, copy and paste the paper. It is not what I want, okay? I need you to generate the signals from whatever the database, from whatever the method you can imagine. And then use the method proposed by the paper, okay, to process your signals and generate some new data, let me say that. And hopefully the new data are consistent, or will be consistent, with that given by the paper. Okay? So you have to go through the procedures in details. If you simply copy and paste the contents, I cannot take that. Okay? I will give you a very low grade, sorry. Okay? So I'm serious about this, and hopefully you are also serious about this. And so that you can enjoy the procedures. All right? Okay? All right, thank you. Question? Oh, by the way, your presentation must be given in English. Okay? So you have to practice. You have to practice before coming to the presentation. Okay, any question one more time? All right? Okay. So I think you all have chosen your topic, right? You all have chosen your topic, am I right? Okay, anyone now has no topic? No? But we have only 5 topics. Yeah, so these are the themes and topics in this class up to this moment. Okay? Now, in case if you are not in the list, you have to let me know ASAP. Okay? Hopefully you can fix the problem very, very soon. Alright? Okay? Gentlemen, did you choose your topic? Have a team member? Yeah? Okay, who is your team member? You are alone. Alpha team. You have a team. So who is your team member? Overray. Where's Overray? Okay, you are here. Sorry. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. Sorry, I forget it. My fault. Oh, sorry. Okay, so I wish you good luck and try your best in the term project. Okay, let's resume the lecture. Going to move to Laplace transform. That's one of the important techniques. Now, the Laplace transform is the beginning or the frequency response, or in the frequency domain. Basically, we treat the problems in two different approaches. One is in the time domain. Another one is in the frequency domain later on. Okay, so suppose you are given a linear system or even nonlinear system. Okay, you have a system here. You have input, you have output. There are two approaches to deal with the problem. One is in the time domain. The other one is in the frequency domain. In the time domain, basically we use differential equations. Okay, we have seen some simple example, differential equations. And that's in the time domain. And in the frequency domain, we are going to use, or sometimes even this domain, or that domain. We'll use say, transfer function. Transfer function. Okay, we will see that one by one. And again, because we're in this one, in the past couple of chapters, and we will see that later again, so don't worry. And this Laplace transform is the technique to use frequency domain method. It's the beginning of the method, okay? So it's kind of important. Okay, in this slide, I think you have done the homework in the very beginning of this course, okay? Suppose we have a sinusoidal signal, e to the s sub 0 times t. Now this s sub 0 is a complex number in general, okay? Then we go through a linear time invariant system. Now this system should be stable. Or asymptotically stable. Okay? In this case, in the steady state, the output can be written as the input, e to the s sub 0 times t, and then times the impulse response, or the Laplace transform of an impulse response. Okay, where does that come from? So here is the approach. Personally, I don't like this approach, because if you just look at the approach, you will think, wow, it is so amazing. It is so unbelievable. You don't get the insight. Okay? But anyway, let's go through this again, and we will see that again later from another different basis. Okay, now first assumption we have to make here is this linear time invariant. And it is the asymptotic state. we simply say that it is stable, which means, okay, later on we'll see that again. The poles of interface are in the left half plane. Of this plane. Okay. This plane. Okay? This is very important. If this is not satisfied, we don't have that conclusion. Okay? All right. Okay, so from the previous analysis, we know the output. The while the output is a convolution of the impulse response and the input signal. So here, use the notation used by the Now, if we are considering total signal, then the lower limit can be replaced by 0. Okay, so okay, just want to remind you, if the x of t is total, that is x of t equals 0, or t is negative. Okay, then while t can be replaced by 0 to h of tau of t minus tau to tau. All right, let me start over again.
Let me switch.
The same. Yeah. If I use the first formula, okay, they are, I think we will prove it in the homework assignment. Okay, if x of t is total, then
We can use this.
the first one, lower limit can be replaced by 0. Okay. Furthermore, h of t is total, which means h of t is 0 or t is negative. Then we can change the upper limit to t. Okay, I use this one, sorry. Let me use this first. Sorry about this. Okay? Because I need the t minus tau. This means t minus tau must be positive. Okay? So t is smaller than t. Tau is smaller than t. Okay, so this is the output for causal signal and causal system. Now let's consider the general case given by the textbook again. So let's consider the second one. Okay, so I use the second, just follow the procedure given by the book directly. Okay. Now this S of 0 can be a complex number in general. Okay? So sigma plus A times omega. So in the S10, in the S10, this is the real axis, and this is the imaginary axis. Okay? So sigma plus A omega will be here. Suppose this is my S of 0, which means the real part is sigma. The imaginary part is omega. Okay? Okay, so let me go back to here. Okay, go. Okay, so if I plug this into the output by using the convolution, okay, so my LP is equal to, so let's consider general case. So the system can be non-causal. The signal can also be non-causal as well. So in a very general case. So h of tau times x of t minus tau. Now x of t is this one, so which means, and then write it down over here. X of t minus tau e to the s of 0. T is replaced by t minus tau. Okay. So this is e to the s of 0. T minus tau. And then times the tau. Okay? And that's equal to the integration from negative infinity to positive infinity of tau times e to the s of 0 t times e to the negative s of 0 times tau and tau here. Now since this dominant variable is tau, so this term becomes a constant term. So I can take it out of the equation. Right? Okay, and then we define this guy, the integration of the impulse response times the exponential function e to the s of 0 times tau h of s of 0. Okay, define this as h of s of 0, and this is equal to and this is the Laplace transform of the impulse response at the frequency s sub 0. So h of s of 0, that's the, we call this Laplace transform. Of impulse response at the frequency s of 0. This is the frequency. Actually, this is the projection, the function of projection. So suppose I have a vector. This vector is a function. Okay, and then I have a unit vector. e to the s of 0 times tau. So this is the unit vector. The product h of times tau over 7 negative. It's a projection, and this is a projection. Of h of tau onto e to the negative h of 0 times tau. This is very similar to vector projection. Very similar to vector projection. Okay? So then you write on that here again. So the Laplace transform is the negative infinity to positive infinity h of tau e to the negative s of 0 of tau and t to tau. So what this is doing is to find the component of the impulse response on the frequency is of 0. So there is that. So this is to determine the component of h of tau on the frequency kind of is of 0, kind of. We can see that much more clearly later on using Fourier transform. So again, if the h of tau is total, then we reduce to integration from 0 to infinity. Okay, this is one side. We call this one side. Okay, if h of tau is total. Okay, and we call this is called one side Laplace transform. One sided Laplace transform. Laplace transform. Okay, and this is the two-sided. Laplace transform. In our course, and later on in your different courses like automatic control, we see one-sided Laplace transform much more open than two-sided Laplace transform. Okay? Because most of the cases we are going to consider is total system. What are total systems? Okay? So today we are going to start from one-sided Laplace transform directly. We are going to start from here. Unless otherwise mentioned, we focus on one-sided Laplace transform. Okay, got it? Okay, I think it's kind of boring, but you have to know that this is very important. This is very important, okay? The mathematician Laplace, he invented this, I think kind of genius. I don't know how or why he can figure this out. Okay? Question? Okay. All right. All right, so here is the definition. Right. The Laplace transform of f of t, by definition, is integration from 0 to infinity of f of t times e to the negative st times dt. Now sometimes we use 0 minus, okay, for the reason that if there is an impulse occurs at time equals 0, then we have to include the function. Okay, if we have a if for some reason you have an impulse at time equals 0, and then later you have some other functions. Okay? In order to take into account this situation, this kind of situation, we start from the equation from 0 minus. 0 minus means it is smaller than 0, but very close to 0. Okay? Very, very close to 0. Smaller than 0. So it's to the left of 0. To the left of 0. Then you can include the Euler function like this. Now the s, like I mentioned before, it is a complex variable. Okay, it includes the real part and the imaginary part. All right, now to simplify the definition, okay, I don't want to get into too much. I just want to tell you that there is a condition for the integration. In order to have the Laplace transform exist, the function we are going to transform must be continuous or piecewise continuous in every finite interval. Okay? And secondly, this function f of t times t to the n is bounded at near t equals 0 for n smaller than 1. This must be bounded at t to the n times f of t with absolute value. At the point, or near the point, t equals 0, when t is less than 1. Number 3, this is the most important one, okay, because most of the cases you need to check this first. If this function with absolute value, or just consider the magnitude of the function, times e to the negative s of 0 times t is bounded for some number of s of 0. So that means you can find a proper number s of 0 such that this function e to the negative s of 0 t times the magnitude of f of t is finite or is bounded. Okay, this is called the function is exponentially bounded. In this case, then the Laplace transform of f of t exists, which also means, okay, this is very important. It must be noted that not all functions have a Laplace transform. Be careful. Not all functions have a Laplace transform. For example, the function 1 over t, does not have a Laplace transform. Okay? And the function, say, tangent of t or e to the t squared does not have a Laplace transform as well. So not every function has a Laplace transform. Okay? I'm not sure, can you find, because next week we are going to have a preliminary, otherwise I'm going to ask you to prove that the function 1 over t, the function tangent of t, and the function e to the t squared, they do not have Laplace transforms. Maybe this becomes the homework assignment for next week after the preliminary report. So I ask you to think about this, okay? This is much more interesting than just memorize the result. Okay? Anyway, so let me remind you here, not every function has a Laplace transform. Especially you have to check this one. You have to guarantee that the function is exponentially bounded, which means if you multiply this function by one proper chosen s of 0, and then this exponential function is bounded. Okay? It's very important. It's very important, right? Okay, so let's go back to the slide here. Okay, so let's go through this example first. Now this example actually is taken from the potential notes directly, but with much more simpler form. So let's consider f of t is equal to cosine omega of 0 times t. Okay, for convenience, let's consider causal signal. Okay, and so we only consider causal signal. We focus on causal signal. So what is the Laplace transform of f of t and g of t? Now these two sinusoidal functions actually come from the same exponential function. Okay, so let's consider another one. Let me put it. L. Okay. Let me say that. So cosine omega 0 t, that's the real part of e to the j omega 0 times t. It says sine of omega sub 0 times t, that's the imaginary part of this exponential function, right? Okay. That's the Euler theorem. So instead of finding the Laplace transform of f of g and g of f of t and g of t separately, let's do it together. Let's do it together. See what happens. Okay, so we are going to look at the Laplace transform of e to the j omega 0 times 2. Okay? That's the definition. So we multiply the function by an exponential function e to the negative st. That's the definition. And then we merge. The two exponential functions merge. The two exponential functions, right? Okay. Now, just for convenience, let me call this A, define A equals to negative s minus j omega 0. So this integration can be replaced by e to the a, e, and e. Am I right? Okay, I think everyone knows how to integrate this function. Gentlemen, could you do this for me? Integrate this function for me. This is a very simple function, exponential function. Come on, almost there. Come on. Okay. Trust yourself, okay? There's an integration, right? From 0 to infinity. Yeah? Don't worry, you're still on the track, so. So what's next? What about the denominator? Okay? Yeah, anyone there? Okay, thank you. Good. Okay, then what happened here? What about this term? Right, that's a problem. That's a problem, okay? But what is A? Again, A is actually I should not write this because this is meaningless mathematically. But that's fine. Mathematically we know what we are talking about. So suppose we have a huge number here, a very big number. Okay? It's multiplied by the A, what is A? E to the negative S minus J omega 0 times a very big number. Okay? Now, this A contains the real part and the imaginary part. So let me write this. This part, e to the j omega 0 times something, that is a complex number on a unit circle. Right? The angle, the argument is omega 0 times theta. But the theta goes to infinity, but no matter how big the theta is, it is always on a unit circle. This is one unit circle. So the magnitude is always one over here. Okay? Now if this S, this theta, this S, if this S is, suppose for simplicity, let's assume it's a real number of a length, okay, make life easier. If this is a negative number, say 1, suppose S is 1, okay, then this is negative 1 times infinity. Okay? So the exponent is a huge number times minus 1. Then e to the negative times a huge number approaches to what? This is a very big number, but with a minus sign. So this equals 1 over, right? So this approaches to, right, 0. So we have a very small number times the number which is bounded by 1. It's always on the unit circle. So when this argument P approaches infinity, then the product approaches 0. So this term disappears, actually. So only negative 1 is left. Okay, but what is this? Okay, let me finish this, and then we get the break. A is negative s plus j omega sub 0 or 1 times 2. So the Laplace transform of this exponential function equals 1 over s minus j omega sub 0. If actually we have a strength for s. But usually we don't care. We assume there is a s which is big enough so that we have a solution. All right, let's take a break and then let me use this after the break. Okay, let's take a 10 minutes break. Okay, think about this. Think about. All right, so in the beginning we have mentioned that cosine omega sub 0 times p, that's the real part of e to the j omega, e to the j omega sub 0 times p. And sine omega of sine omega sub 0 times p, that's the imaginary part of e to the j omega sub 0 times p. Okay? So let's combine what we have here. So we have Laplace transform of e to the j omega sub 0 times p equals 1 over s minus j omega sub 0. Okay, up to this moment. And we want to determine Laplace transform of omega, cosine of omega sub 0 times p. So that's equal to the Laplace transform of the real part of e to the j omega sub 0 times p. Okay? And here is the jump. That's equal to the real part of the Laplace transform of e to the j omega sub 0 times p. Kind of a switch the two order. Kind of, because okay, I'm a little bit sloppy to prove this. We are running short of time, so we have shown you the Laplace transform of this exponential function is s minus j omega sub 0. Okay?
So what we have to do now is
You rationalize this. this is equal to S plus J omega sub 0 S squared plus omega sub 0 squared. Now, for the moment, okay, just kind of symbolically, let's assume S is the real number. Actually, it's a complex number. We just want to make our procedure easier to proceed. Okay, so this is equal to the real part of S plus J omega 0 and S squared plus omega sub 0 squared. Okay, look at the numerator. The numerator is S plus J omega sub 0. So we take the real part. So that's the S over S squared plus omega sub 0 squared. Okay? So that's the Laplace transform of the cosine function. Likewise, the Laplace transform of the sine function. Okay, now we have to take the imaginary part. That's this part. So that's equal to omega sub 0 over S squared plus omega sub 0 squared. So it's much more easier to find the Laplace transform of cosine function and sine function than using the definition to find the Laplace transform of cosine and sine function much more faster. Okay, so that's the trick. That is the trick. If you use cosine of omega sub 0 times t here, if you replace this exponential function by cosine of omega sub 0 times t or sine of omega sub 0 times t, and try to integrate the function, it is much more complicated and involved. Much more complicated. Okay? So this is a shortcut. Okay, got it? Yeah. I just assume here. Here I just assume S is a positive number, then that's fine. If S, well actually the real part of S is bigger than zero, then e to the negative S times t approaches 0 and t approaches infinity. Right? Okay? So I let just for simplicity, just an example, make you easier to imagine what happened. Okay? Yes? Say again? Which part? This one? Oh, because the new denominator is S minus J omega sub 0 times S plus J omega sub 0. So that's equal to S squared plus J omega sub 0 squared in the denominator. So this is equal to, I'm sorry, confuse myself. Yeah. Okay? Got it? All right. Okay. All right, so this is only a typical example to simplify the procedures for searching the Laplace transform of for certain functions. But later on, you will see that usually we don't use the integration to find the Laplace transform because someone already did that for us. Okay? Let me put that. If you look at your book, look at the textbook, okay, or look at any other tables, you will find, well, not some. Okay, look at this one first. You can find people already did the integration for us, so that we can take the advantage just by looking at the table and then find the Laplace transform of a certain function. Now, those are special functions. I need you to memorize them, burn it into your memory. Okay? So when people ask you, well, what is the Laplace transform of a given function, you have to tell me that that's 1 equals 1. One side is Laplace transform. Okay? And what is the Laplace transform of a unit step function? That is 1 over s. 1 over s. What is the Laplace transform of a unit ramp function? That is 1 over s squared. What is the Laplace transform of e to the negative a times t? Now here, in general, this a is a real number, but it can be a complex number, as you just did. Okay, so the Laplace transform of this e to the negative a times t, we consider t is bigger than 0, so we can see the photo signal here. Then the Laplace transform is s over 1 over s plus a. 1 over s plus a. You have to burn that in your memory. And then we just did this. The Laplace transform of cosine omega sub 0 times t, that's s over s squared plus omega sub 0 squared. Right? Okay, we just did this. And then the Laplace transform of sine omega sub 0 times t, that is omega over s squared plus omega 0 squared. And we also just did this. Okay? Those functions, 1, 2, 3, 4, 5, 6, I need you to memorize the result into your memory, into your supercomputer memory. Okay? You have to memorize the result. That will help you a lot. So one more time, the Laplace transform of a delta function is 1. Laplace transform of a unit step function is 1 over s. Laplace transform of a unit ramp function, that's t's unit ramp, is 1 over s squared. Laplace transform of the exponential function e to the negative at is 1 over s plus a. Okay? Laplace transform of the cosine omega 0 times t, that is s over s squared plus omega sub 0 squared. And finally, Laplace transform of sine of omega sub 0 times t, that is omega sub 0 over s squared plus omega sub 0 squared. Okay? So those 6 functions are the basic functions you have to remember. You have to memorize it into your supercomputer. You have to burn it into your supercomputer memory, no matter what. Okay? Got it? All right? And in the meantime, there are some properties for the Laplace transform, okay? And due to the time limitation, and also the focus of this course is not to derive the mathematical formulation. So I'm going to leave this to you, and this can be your homework assignment in the next week, okay? So you have lots of to do in the next week, okay? So for example, the Laplace transform satisfies the linearity. Okay, we have just defined this in the class, right? Linear function. And time shifting, frequency shifting, derivative, integral. Okay, I need you to memorize this. Because we are going to use it quite a lot. The integration of a function in time domain, integral, right? In time domain. In the S domain becomes more equivalent. In the S domain is F over S. F is the Laplace transform of this time function. Again, in the time domain, we integrate a function. Then in the frequency domain, that is F of S over S. So symbolically, we use the clock variable 1 over S to represent the integration. Okay, in the time domain, we use the integral of a function, right? But this is equivalent to 1 over S in the frequency domain or in this domain. You have to memorize this. So if we take Laplace transform, the Laplace transform of this function is equal to suppose F of S. Then after integration, this becomes F of S over S. Okay? And then there is another derivative yes. If you differentiate the function in the time domain, df over dt, that is equivalent to you multiply the function f of s. F of s again is the Laplace transform of f of t. You multiply f of s by s. So this is again, if I have a function f of t, in the time domain, if you try to differentiate the function, then in the S domain, you times S. Sorry. You multiply the f of s by s. So this is f of s. So this is equivalent. Okay. Again, okay, let me refresh a little bit, rewind a little bit. In the time domain, if we integrate a function that is equivalent to in the S domain, we multiply f of s by 1 over s. So whenever you see this symbol, 1 over s, this means it is an integration. Okay? And also for the differentiation, if you differentiate a function in the time domain, that is equivalent to in the S domain, multiply f of s by s. Okay, so whenever you see a block diagram, s, that means it is a differentiation, derivative or differentiation. I prefer to use differentiation. Differentiation. Okay, it is a differentiation. Right? But mathematically, if you take the Laplace transform of this derivative of f of t, you have to include its initial condition. Okay? If there's a non-zero initial condition, this must be included. This must be included. But for most of the cases, we are going to consider this will be zero. Okay? This will be zero. If the system initially is at rest, initial condition is zero. Okay? But anyway, symbolically, we all take S in the S domain, S as a differentiator, Okay? So that's a convention we use in the block diagram, especially called automatic control. So you have to know derivative, integrate, and integral. Derivative and integral. Those properties. And then for the initial value, okay, the limit t approaches 0 is equivalent to the limit s times f of s. S approaches infinity. We need to prove it. I'm not sorry. No. I need you to prove it. Not me. I need you to prove it. Okay, so this will be your next week homework assignment. Next week's homework assignment. You can find a proof in many different books. That's fine. And also, there is another very famous theorem, very important theorem, final value theorem. Compared to the first one, the previous one, that's that. Here we have a final value theorem. Okay, this is initial value theorem. But we also have a final value theorem. They look very similar, but this one is the steady state. The steady state of f of t means when t approaches infinity, it is equal to the limit of s times f of s as s approaches 0. Okay? And actually this is to find whether the system or the signal is specially treated as a signal. If this signal has a unit step or a multiple of unit step function, this is indeed trying to find whether the signal has a unit step function in the signal. Okay? So mathematically it's very easy to understand this. But again, I need you to prove it in the next week assignment. Okay, so due to the time limitation, I am not going to give you the proof in the class. Okay? Sorry about this. All right, so let's move to the next part. Now, when we try to find the inverse. Okay, maybe before that I have to define something. Okay, so let's define the pole and the zeros first. And this is a very important terminology. If I have a function, f of s, which is the Laplace transform, okay, let me define that. Let f of s be the Laplace transform of f of t, and that's equal to n of s over d of s. Okay, n of s and d of s are polynomials. In general, are polynomials. In terms of s. And of Si equals 0. Okay? And zeros. Let me use PI. Sorry, let me use PI. ZI. Okay, let me say that again. Suppose I have a Laplace transform of a function f of t. F of t is supposed to be integrated by using the Laplace transform. And suppose there exists the Laplace transform of f of t. And after transformation, we have n of s over d of s as the Laplace transform of f of t. Now the pose is the point
Such that P of T of line equals
0,
line to be 1, 2, 3,
where the number is. Okay, and this is j, and this k. This depends on the degree or order of the polynomial. Okay, we will see that later. So, what can I say about the pose? Okay, note. O PI determines the stability of the system. If f of s is the transfer function, later on we will see that, of the system. Of the system. Okay? So a quick example again. Right, let's reconsider this case. F of s is equal to 1 over s minus a. So in the S domain, it means it is in S domain. This a can be at real axis, negative real axis, can be right at the origin, can be in a positive real axis, right? Okay, but then so the inverse Laplace transform of 1 over s minus a is e to the at. If you look at the table or whatever the method we use. So you can imagine that if a is here, what is the response? It's going to be a. Right? If a is here, if this is a, if a is here, it will be a, but slowly. If a is here, that's 1 over s. what is the corresponding time function? 1 over s. That's a unit step function, right? So the response will be 1. That's unit step function. If a is here, then it's going to be exponentially growing. If a is here, it's growing much slowly. It's going to grow very fast, much faster. Right? Okay? What about that's okay. Belongs to the set of real numbers. What if a is here? This is J omega axis. That's the imaginary part. Okay? If J is here, okay, that means we have FRS. So the corresponding function now, even though this is a pure imaginary number, but we still can use the result. So it's a sinusoidal signal with real part and imaginary. Okay? And similarly, if it is here, the same. So we can combine all the results we have just considered. Then we have this very beautiful figure here. If the pole, we call this pole, is here, then the corresponding time function is exponentially decayed. Okay? If it is here, it's also decayed, but with a slower rate, slower decaying rate. If it is right at the origin, that's unit step, 1 over s, right? So that's unit step, constant. If it is in the positive real axis, it is exponentially growing, Okay? Now, if it is right and the j omega axis is a sinusoidal wave, sinusoidal signal. Okay? Here, also sinusoidal signal, but with a higher frequency. But if you have a pole at this point, which includes both real part and imaginary part, so we can imagine that it's going to oscillate and also exponentially decay. Okay, if you move to here, it's going to oscillate and exponentially decay, but with a slower decaying rate. If it moves to the right side of the S10, suppose it's here, then the signal is also going to oscillate, but with the amplitude exponentially growing. Okay? If you move up a little bit, then it's also exponentially growing. Okay, but the frequency is higher frequency. Oscillating with the higher frequency. Okay? What about this point? Those are we call this simple post.
There's another one which shows if we have a double pole,
What that means, we have a repeated loop at origin. What will happen? Suppose my f of s let me open another small window here. So if f of s is 1 over s squared, then the inverse Laplace transform. Can anyone tell me what is the inverse Laplace transform? The time function. What is that of p? I'm sorry, this is so sorry for this. It should be inverse Laplace transform. So what is the
inverse Laplace transform.
or 1 over s squared? If you look at the table, that is what? Which is equal to 1 over s times 1 over s, right? 1 over s means it's an integration. We have already known that the Laplace transform of the unit step is 1 over s. So you multiply 1 over s by another 1 over s means you integrate in the time domain, you integrate the unit step, which gives you the rank. P is positive, so that's the rank function. So it is useful. So in S domain, if I have a double pole over here, okay, double pole S, the poles are S equals 0, S equals 0. That's what we call this double poles. Then the corresponding function is P. So the function becomes, the corresponding time function is P, so it's unstable. Okay, so it's P. So if you have a double pole at the origin, then
The corresponding time function is P.
okay. Now, what about if I have a double pole at the j omega axis? If I have a double pole at j omega axis, what is the corresponding time function? So I need you to, do we have time to do this?
Run the
Laplace transform using MATLAB.
laptop. Use MATLAB to find the inverse of our transform of this function. Confirm that it is equal to this. 1 over s squared plus k squared, quantity squared. Okay, use your laptop. Now, open your laptop. How to use MATLAB?
To find the Laplace transform or inverse Laplace transform, there are some sample examples here. Yeah, you can start from running the sample code. say 3.2. Okay, and 3.4. Especially 3.18, 19, and 21. So in these examples, the method tells, excuse me, tells you how to find the corresponding time function or corresponding inverse Laplace transform of those transfer functions. So I need you to follow the procedures and then find the inverse Laplace transform of the function that I gave you. Okay? Please do it now and tell me what you find. Okay? Now, especially this example, the last one. For example 3.1, 3.18, 19, and 21. These examples tell you how to find the inverse Laplace transform of the following three transfer functions. Okay? And the transfer function that I need you to find is this function. Again. This one. Confirm that the inverse Laplace transform is the right hand side using the symbolic angle. Using a symbolic angle. Try to run the sample code first. Try to run the sample code first. The purpose of this function is to let you know that what happens if I have a double pole at the j omega axis. What is the corresponding time function? It is supposed to be something like this. Also exponentially growing. I mean the amplitude also exponentially growing with a frequency omega. Okay, but it's multiplied by the function t. So becomes the amplitude becomes bigger and bigger and bigger. Try to run the sample code first. Start on an easy one, okay? And then once you are familiar with the symbolic toolbox, symbolic variables, and then we can move to the dust example, okay? Especially you have to know how to call the Laplace transform and how to call the inverse Laplace transform. The first three examples is about the Laplace transform. The last example involves not only the Laplace transform but also the inverse Laplace transform. Okay, Laplace transform. That's the inverse Laplace transform. Okay, so try to run the sample code. And after you are familiar with that, then you can modify the code to find the Laplace transform of the function that I mentioned. Try something? It's on the page 224, 222.
223.
Start from 223, and then 224, and then 225, 226. 27. In these examples, you learn how to use symbolic variables to declare a function, time function, and then to declare a transfer function in S domain, and then use the Laplace command to find the Laplace transform of a time function, and use I Laplace to find the inverse Laplace transform of a transfer function. From example 3.2, and this is the easiest, only a few commands. Define the just symbolic variables first, and then define the heaviside function. Let's use the unit step function. Okay, and then take the transform of the unit step function. So you are supposed to find U equals, capital U equals to 1 over S. And then define direct delta function. Direct C, that's a direct delta function. And then take the Laplace transform of the function. So this capital D is supposed to be 1. Okay, and then the rectangle pass. So the second term is heaviside function of UV step delay, T minus 1. We haven't talked about the delay, but we are going to talk about that later, next time. Did anyone finish the first one? 3.2. Got it? Okay, good. Did you finish the first one? 3.2. In the second example, we are going to find the Laplace transform of those exponential functions and cosine function. You put your cell phone in your pocket for a moment, okay? Did you finish the first one? transform of e to the negative t should be 1 over x plus 1. Okay? And this will be x times cosine of the exponential function e to the negative t times cosine of n t. So the Laplace transform here we involved would be, it'll be something like s over s plus 1 quantity squared plus n squared. Okay? So if you have finished the first 2 examples, then you may move to the last one, okay, the third one. This one, you are going to find the inverse Laplace transform of different transfer functions. Third example, you also need a function PFE Laplace. Okay, it's given by this function on page 230. PFE Laplace. That's a partial fraction expansion, but we haven't talked about that, but that's fine. We will see that later again. Finish the first 2 examples. Look different. Some of you made a change to the program. You may leave now, okay? It's already over 60.
Oh.